can get started with today's QuTech360. I'll be chairing today's seminar given by Carlos Errando Herranz, who is a almost sorry about that. So he's a group leader in the Quantum Internet division, and today he will present his work on building blocks of quantum information processing with color centers in silicon. Take it away, Carlos.
Thank you. So thanks everyone for being here instead of being outside in the nice day it is today. So I really appreciate it. This seminar is going to be a little bit different than the ones you're used to. We are going to be, I hope that there's going to be some deep interaction here. And we will start actually by you scanning this QR code. I need your phone. Don't go into WhatsApp. Don't go into your emails. This is a little experiment that I have been trying in a few different workshops and seminars, and I really have high expectations for QuTech. Exactly. Are we there? Are we good? Okay. So we start with a simple question. I guess this one, you know it, I hope. What is your career state? This question, I just use it because then I would like to do some statistics and compare a little bit, especially as a nice way to shame group leaders. I think here it's only Christian. So you're going to be, I know exactly what you answer now. Good luck. Okay. We got, yeah, nice, about 50 people. Yeah, that's going to show me the results, which is Kristen. Good. Okay, so I'm going to start with what I started calling a classic PI move, which is talking about something I don't really know. And that's going to be quantum information theory. I'm actually myself an engineer, so quite far away from that. This is a little more on the computer science. So theoretically, you should be getting the question on your phone. What can we say about quantum computing? We're shy of 10 people. These are maybe questions that look easier than what they actually are.
Well, traveling salesman. I don't understand.
Okay, that's a question that I thought I didn't have to answer, but yeah, it's a, let's say, a complicated problem of optimization. Okay, let's see what came out. Nice. Okay, so we are quite clear that it's not faster than classical computing in any task. That's good. That's sounds reasonable. But there's a lot of people saying that it can solve the traveling salesman problem and can solve all problems solved by a classical computer, although this is not as high. By the way, something I forgot to mention is that you could have answered multiple answers. I hope that was, yeah. But maybe for the next ones, you know. Okay, so there go all my high expectations for QuTech. So the point of this question is actually, I'm not an expert on this, but I wanted to basically, I wanted it to be a little bit of a wake-up call for people working with quantum technologies to look into the theory behind the stuff that they're trying to do, right? Meaning that you're trying to build a quantum computer, let's say, or a quantum network or something. And there's a lot of hype out there. There's a lot of things that we are told that these things can do. Not all of them are correct. And one of them is the traveling salesman problem, actually. So if you're familiar with complexity theory, I don't know how many people are familiar with this, more or less. Okay. So we have this subset, this class of P, which is problems that we have algorithms for solving them with a classical computer in polynomial time, meaning like easily, right? Then this is a whole kind of set of this. You can imagine a lot of points here with different problems, and then P we can solve with a classical computer. BQP is what we can solve with a classical computer, the quantum computer, sorry, efficiently. You can see that it's a little bit, bumpy. It's a little blurry. That's because we don't know a lot of things about that. And there's a very few algorithms that people have developed. So that's why it doesn't look really nice and complete. But this kind of applies to a lot of other problems. So the point here is that BQP is containing P, and that we know, right? So the third answer before of can solve all problems by a physical computer is correct. And I guess you can also know that by intuition, right? You can say like a qubit and a bit, right? You can collapse a qubit and get a bit, and that should work. But a problem like the traveling salesman is actually a NP-complete problem, which are very important problems that map into each other, meaning that if you have an algorithm for solving that, you can solve all of them. And it is not proven, at least, that quantum computers can do that. So, and this is very important. Everyone answered the wrong thing in this case, right? So the point here is try to look up complexity theory, because this is very important for the stuff that we are doing. Yeah, so there are, again, a lot of these things are not maybe set in stone, right? There's a lot of questions, but there's also a community consensus that we should really be aware of as quantum scientists. So I hope that helps giving you something else to think about if you didn't have enough things to think about for your PhD. Next question, similar to that one. Once we have useful quantum computers, what will we be able to do? Okay, I'm gonna be moving on. All right, nice. Okay, so that one is better. So we can factor large numbers. That's nice. That's, I guess, the most well-known algorithm, right? That shows factoring, simulating atomic interactions. Nice. Perform more efficient computation, optimization, somewhere there, and also perform parallel computation. So in general, people are saying more or less everything, right? And maybe this one a little bit less. It's good that this one is a little bit less, because that's actually the one that is the most wrong in here. But maybe to summarize, I just took this very recently from our friends in Amsterdam, from a recent book that's also on the web, this Introduction to Quantum for Business or something like that. And it's actually nice because it's a very nice sober view of what one can actually do with quantum computers. And they are splitting this in the different things that we can do in these different ways. The ones that before we were calling it BQP are the ones that are here, right? The exponential speedups you can get with a quantum computer. And you know the Shor's algorithm, and there is also some good, at least good intuition that we can solve some chemistry and material science problems with this. Now we have the polynomial part, which is Robert's algorithm. Many people are familiar with that, also relating to optimization and so on. The issue with the polynomial speedup is that it's polynomial. And that's tricky, because if you assume that quantum computers are hard to make, and that they don't run as fast as classical computers, probably, as we are at least figuring out now, maybe in the future is very different. This polynomial speedup is not really a speedup, right? Because you already need polynomially more resources to make a quantum computer, or to make it work, or to run it in terms of time. So your speedups kind of compensate to nothing, right? So that's why when computer scientists talk about these sets, they talk about exponential speedups and not polynomial. And then we have some other problems that we know there is no speedup. And then there is this cloud here of heuristic problems that we don't really know if they actually fit. There's not a theoretical proof that they have an exponential speedup. There's a mathematical proof of that. But people are trying to see whether they can find like experimental proof that this can be done faster with a quantum computer versus with a classical computer. And this includes annealing or variational quantum circuits, some other chemistry, material science, and a bunch of other things. I hope this is clear. This is all I wanted to say about this part. And now we're going to be moving a bit more to practical things with with the field that I'm actually working on, a bit more towards the physics and engineering. But I hope this was useful for you to know what you don't know. And I think it was rather clear from the answers. Okay, so the content of my presentation, I already talked about the first point. And now it's a little bit decoupled, but I really wanted to do this experiment. And now we're gonna go into color centers. So how do we do quantum information processing with color centers? So for people that are not familiar with this, color centers are a poor man's atom in a vacuum, right? So we like atoms, but if they're in a solid state in a crystal, then we can manipulate them better. That will make our life much easier. And the question that I have now for you is actually, why would we like them? And hopefully you don't know this question very well, actually. This is a question that I hope you will answer wrong, because otherwise a lot of the stuff I was saying in the slides, it's not going to be so useful. Yeah, I expect most people to answer the last one, by the way. I mean, we are a QuTech, right? So everyone has their own qubit. Get them under the pillow. Okay, are we moving on? I think most people are still answering. That's good. Nice. Okay, I expected this one to be really high. Now I'm really disappointed. Okay, so they host qubits with long coherence times. Nice that people are quite okay with that one. Great photon emitters, quite high. We have all the components we need for complex quantum systems there, and high entanglement fidelities and the photon loss. Good. Okay, so I'm going to be talking about all of these things in the next slides. So the first one that I wanted to talk, especially for people that are not familiar with how we plan to use this or how we use them, is how we'll be able to compute with a color center network. This kind of applies also to quantum communication. But I'm going to take it, since we were talking about computing before, I'm just going to take it from that computing side. This is just one example of how one can compute with these sort of resources. And this is one-way quantum computation based on measurements. It's not the only one, right? So this is just a way that I want to show how, with a very clear, hopefully, example, one can do computation with color centers. So this one is going to be a little bit hand-wavy. So we start with entangling the network. Easy, right? The step number 2 is when we have an entangled network, then if we can write our input qubits, our set of qubits, then we can set right in a specific state. And then if we can use measurements to consume this entanglement that we have created before, and by that we will be computing. So I didn't plan to go very deep into this. You can look at that paper if you're interested on how this would be done. But this is, I think, a rather common approach to computation for a number of different hardware, types of hardware, including photons and color centers. So yeah, sounds easy. Just 3 steps, right? So how will we start, actually? And the trickiest step, as you may have imagined, is the first one, right? Like generating a large entangled state is hard, right? And that we know. That's a pretty hard thing to do. So how do we do it with color centers? And this is a walkthrough through the Barrett-Cook protocol, which is one of the, I think, a nicely visual protocol that we use with color centers. So we start with this system. So we have 2 color center qubits, which are represented with these 2 orange dots, and they have these sort of energy levels, right? So you have spin, and then one of these spin levels is coupled with a photon, so that if you excite that with a pi pulse, then you get a photon out only when you're in this state, right? When you're spin down. So you basically have spin photon entanglement in your system, right? And then we have a beam splitter, and we have single photon detectors that just give you a click if you get 1 or more photons in each of them. Okay. So what's the goal? The goal is to entangle those spin qubits, right? So we have each of the color centers will have a spin degree of freedom, right? And you want to have them entangled, and you want to have that state. And the system that we have is, as I mentioned, atomic like qubits, so spin optic interface like color centers. What are the assumptions here? So we can initialize our qubits for this protocol, right? That's the assumption. And we do that actually practically with some optical excitation and some measurement and microwave control of the spin, which is just running microwave pulses through. We can do single qubit rotations again through these microwave transitions that separate those spins when we split them with a magnetic field. And it assumes that we have linear optics, which is a pretty good assumption because under low power you have linear optics in most of the cases. So, okay, this slide is a little more complex and I actually don't plan to go through it, but this is how the protocol looks like. So you basically set a specific state, you run a certain optical pulse, and as it goes through the beam splitter, you can measure clicks or not measuring clicks in these detectors, right? And then only when you do this measurement, this protocol, these 2 steps, and you measure clicks in both steps, then you can say that you have an entangled state, and that's a heralded entangled state, right? So I'm not going to go into that, but yeah, the green ones is when you have a click. So then you can see that the way you are doing this protocol, you're basically trying to reduce the amount, the times that you will get an infidelity from no photons being there. Okay, so now what are the good and bad sides of this? So the good sides is that we can get, if we have a heralded entanglement, we can get fidelities that approach 1. Because only when we get these 2 clicks, then we can say, okay, this means that we really had that state in there, right? And I will go to the caveats a little bit better. And the photon loss, which is a really big problem, because everyone that has worked with optics, you know that things are just lossy, right? You lose photons all over the place, right? In your fibers, when you have any connection, when you have a device in the middle. So if you have photon loss, it only reduces your rates, the amount of how fast you get entanglement, right? But it doesn't reduce your fidelity. And this is very important because, again, like optics is lossy. And if we have a protocol that having loss reduces your fidelity, then you're in trouble, right? What are the issues? Well, the issues come from actually doing this, from the experimental parts, right? So if your detectors click when they shouldn't click, that will give you that would be a problem, right? Because then you will be thinking you have entanglement when you don't have it, right? So that means your fidelity goes down. And that can be from dark counts, meaning that the detector just out of heat, right? Around there, they just click, right? Or leakage counts, meaning that part of your laser that is supposed to only excite the color center, but not anything else, if it just finds its way, right? A photon of your laser finds its way into the detector, then you have a problem. Then, because of this splitter operation that we need quantum interference, if you have photon distinguishability, so your color centers are spectrally different and they don't interfere in the way you want them to interfere, then that will also mean that your fidelity goes down, because then you can distinguish path information, and then you cannot perform this protocol. And then the other issue is that the rates just may be low in general, right? That's not a problem for fidelity, but it's a problem for rates. If you have a nice entanglement protocol that gives you one hertz of entanglement rates, that's probably not super useful, right? Okay, so I will keep using this orange text in the slides to highlight what goes into this Barrett-Codd protocol in entanglement, fidelity, and rates as we go through the actual devices. Okay, so now we have talked about the protocol. Now let's see what do we actually need to build it, and that's the main part of the talk. So I'm going to be talking about building blocks, and it's going to be a little bit of a run through a lot of stuff that I have been doing in the last years and that we are getting out recently, mostly from work that I have been doing before my time here. So mostly from MIT, a little bit from my time at KTH in Stockholm. So what are the building blocks that we need for a quantum processor, let's say, generically, right? Quantum network or quantum computer. So we have all the controls up there. I'm not going to talk a lot about that. I leave that to people like Fabio or Masoud or people that are working with these cryo-electronics and the FPGA and so on, but there's some control that is very critical to do there. And then I'm going to be talking mostly about this row here, where we have qubits, the switches, filters, and the detectors. And the laser in general is something that we can keep outside in most of the cases, so we don't care too much about it. We just need a fiber going in, and the laser can be somewhere else, and we don't have, at least at this point, very strict requirements for that, for developing that within this research on quantum technologies that we are doing. Okay, so before going into those details, I'm gonna talk about silicon a little bit. So why do we like silicon? And I guess that's very clear for many people. We can do very good fabrication in silicon. We can have the most advanced integrated photonics, and I guess many people here are not coming from that field, but we can get all of these things kind of for free in silicon photonics. We can literally just order a chip that has a lot of very, very cool, very optimized components that will work for doing a lot of this optics processing that we need to do. Something that is partially missing, especially when you work at cryogenic temperatures, is the reconfiguration and the detectors, and I'm going to be talking about that in the next slides. So then we have microelectronics, of course, it's great, like everyone knows that. And something that is also very crucial is that we have silicon-28 as a super clean material that we really like, because in terms of spin, it's a vacuum, right? It's something that can be, especially the one that people are doing here, for example, like Giordano's group, is really, really good. And this has resulted in extremely long coherence times for spins in these materials, right? Something else that is great is that we can also find color centers in silicon that emit at telecommunication wavelengths. And that's really nice, right? Because that will save us a lot of headaches. So starting from the qubits, we will start with the color centers in silicon. So this is not work from me, from my group. This is something that this is how the field kind of got started. So people started by isolating single color centers in silicon, in a piece of silicon, basically, and they were seeing some photoluminescence from specific spots, right? So you shine in with light, you get infrared light out, and then they see that this infrared light that they get out is single photons, right? So this first measurement, I'm not going to go into details. I'll explain a little bit later about how that works. But you basically, it shows that you have single photons, and this is the spectra. You can see that there's a nice peak here, which is the coherent emission of this color center, and it's emitting within this band, which is the telecom O band, right? Which is the one we are using for the internet, right? The internet going to your home is coming at this sort of wavelength, O band and C band. So those wavelengths. And then this color center actually is not known to have a spin in the ground state, so that's not great for our protocols, right? But we have, there was the T centers, that was another color center that was discovered a couple of, or isolated a couple of years later. And then there they show that we can get also a ground state a spin in the ground state. Okay, so what are the challenges now if we want to do these entanglement protocols? So we have a few different challenges. We have to integrate them into photonics to increase the complexity and scale up the system. We have issues with the line widths. And I'm going to explain what that is later on. We have emission. Again, if the rates are low, you don't get any entanglement. So you need to really pump up this. You need to form them in a high yield, in an efficient way. And you need to spin control them. I'm going to be focusing mostly on the first four because I haven't worked a lot with the spin control. So if we start from integration into photonic circuits, this is something that I did together with, of course, a lot of very good people back at MIT. We published it in 2023. So what we got here is, for the first time, we managed to fabricate single color centers in silicon waveguides. So meaning that then you can combine all these photonics that we are talking about with the color centers. And in this case, we were looking at G centers, which is one of these color centers. The one that I was saying before, a lot of the work that I'm talking today about is going to be about G centers, and that's basically just because it was the easiest color center to make in silicon. But a lot of these things, in principle, they extend to any other color center that you would have in silicon, like the T center that I mentioned that has a spin, or even potentially other new color centers that may be more exciting. So here we talk with we're dealing with the G center. So the G center is 2 carbon. It's a defect in a material. So you have silicon atoms there, and then you have 2 carbon in a place where there should be 1 silicon, and then you have a silicon interstitial also there, right? And that's the defect. And this defect has some certain energy levels, and then some of this ground unexcited state, they give us these nice photons in the telecom O band. So this is the wavelength for the telecom O band, and we see that through the photonic waveguide. And then we did these experiments to measure that we have indeed single photons coming out of this waveguide, and this we do by basically exciting the color center. It emits single photons, and then we send the photons that come out. Sorry, I didn't explain how we did this, but we're exciting from the top with green, and then we get the photons coming out, and we're collecting them through a fiber here, right? And this is the waveguide. So we get the photons through the waveguide, then we send them to a beam splitter, and then you can imagine that if you have single photons, when this distance here is the same as this distance here, you should never see a coincidence between those detectors, right? The photons should be either in one arm or the other, right? At that time, they could never come at the same time in both because you have only one, right? And that's what we see here. It's a little bit of a dirty plot, but you can see that when this time delay between those two detectors is 0, then you get a nice dip here that shows that you have indeed something close to single photons. Next challenge, homogeneous and inhomogeneous line widths. And I'm going to explain this mostly by saying that what people actually wrote, you guys answered before, that color centers are great photon emitters, and that's not entirely true, actually. They are photon emitters, which is nice, right? But they are not great photon emitters. And one of the reasons is this inhomogeneous line width, meaning that this is actually a plot from the previous paper where we took some statistics over different color centers that we're finding in the waveguide. And you can see that if you look at the coherent emission, it's actually offset, making this Gaussian distribution, right? So we have a bunch of color centers here, a bunch of color centers here, a bunch of color centers, right? Like that. And it's giving us this distribution. That's bad, right? Because you would like to have them all in one super narrow line, right? And that's not what we're seeing. And that's coming from environmental inhomogeneous strain. Different color centers are living in a slightly different block of silicon, right? They will have maybe different defects around them that is straining them in a different way. And that gives you this broadening. So this means that statically, each of them is just slightly different. And this is about, in our case, for the G centers that we measured, was about 1 nanometer. And this will limit severely entanglement fidelities, right? So what we did for that, this is something that the paper that we put out in the archive very recently. We tuned the strain on these color centers. It's something that people have done already in other platforms. It's just that with silicon, it's kind of much easier and nicer. So what we see here is the first experiment where we had this cantilever. So this is a waveguide that is suspended. And then we have this suspended beam here. And then we can charge this towards the substrate with these electrodes in there. That means that we have a potential between this and the substrate, which will mean that it's going to have an attractive force, right? And then it's going to be bending. Okay, that was the model. By bending it at this point here, you get a strain. You're basically stretching it a little bit, right? And you're bending. And by doing that, if you have a color center there, then you're going to be shifting your emission wavelength. And this is what we see here, right? So we have take one of these lines. These are 4 different color centers in that spot, and then we see how they are shifting, right? You see them going in, shifting in different directions. So this allowed us to do reversible tuning. So we are straining them, and we can strain them back into alignment within this 130 picometers, which is about a bit more than 1/10 of the inhomogeneous line width. So you can see that there is some room for improvement here, right? But we can at least within that 1/10, we can probably align already many of them by doing this. Something very cool that I'm not going to talk about is that by doing this, we also figured out, actually I wanted to say that this work was done in collaboration with my student Matteo, who's sitting there actually. But we figured out a very cool way to do nanoscale localization. So if you can do this and you can actually if you get all the information you can from this system, you can gather from this system, we can know actually where these color centers are in the vertical direction within 3 nanometers, which is pretty cool actually. And we can really go almost down to the single atom in the crystal, right? Where it is, which we are planning to build on that in the coming years. All right, so next step, emission enhancement. So again, color centers are great photon emitters, not really true. Oops. Yeah. they are actually quite good. Okay, yeah. So they are not really, it's not really true. And the reason is that there's a lot of factors that actually reduce their rates, the emission rates. So in principle, you will expect that if you have a perfectly emitting color center, you will have lifetime limited rates, right? So every time you emit a photon, then you can emit another photon, you can emit another photon, right? So you have, that is the limit. And for example, if you go for the T center, that will be 1 microsecond, that will be megahertz rates, which is already kind of slow, right? But okay, like let's say you are happy with megahertz rates. Then you have quantum efficiency, so other states that may be coupling to your states. And that will mean that a lot of the times you actually don't get the right transition. And you can have this phonon induced decoherent paths, basically, which is quantified as the Waller factor. And you can see that all this is basically almost 2 orders of magnitude. And you're not even looking at loss in the circuit, right? So that is bad. That means that you go from megahertz rates to kilohertz or below, right? Which is starting to be really, really tolerant. So the way we address that is with cavities. So if you engineer the electromagnetic environment around your color center, then you can pump up those emission rates. Can do a number of other things, but I'm just keeping it simple like that. So what we did in this work, also at MIT, was to build this photonic crystal cavity. So we did some inverse design for making very, very nice cavities, at least in theory, that will have nice vertical coupling and a high quality factor versus volume, which is what you want for this. And we coupled them to single color centers in commercial silicon. And we got these values leading to a relatively not very high percent enhancement, but it was good enough to show that we are actually enhancing the cavity as we move the cavity towards the color center. You can see that you have some more counts there. And we use that to also bound the G center efficiency to 18% for this specific color center. There's a lot of work to be done here. This is a very preliminary kind of result that just show that we can enhance them with cavities, but we need to do this better. Okay, next step, how deterministic formation. We need to be able to make these color centers in the right place. And this is something that we started to look at also at MIT. You can see people making the MIT logo with dots. It's a classic. So this is basically just shining light, focused light into your sample and seeing whether you can make color centers if you have a sample that's already doped. And we did that with a carbon doped sample, and then we could form G center ensembles in bulk, and also we could make them in cavities. So we can actually fabricate a cavity, then we can shine light on it, and we can see how by shining light at a given power, we can see this peak coming up here. That is aligned with the cavity, which is the transmission of the cavity. And the nice thing also that they worked on that heavily, especially Wu here, was to make it controllable and predictable via building a digital twin of the system. So kind of trying to get some sort of pseudo black box approach to understanding what's going on behind this. Okay, so what's the next step? What's the next steps for the qubits? It was a lot of information in quite a short time. I hope it was more or less clear. You need to integrate qubits into complex photonic circuits. What we showed before was just a waveguide, right? It's the simplest thing. And there's a lot of things that we need to do that. You need to deal with also the homogeneous line width, which is a very critical one, meaning that you have your color center that can be like jittering, right? Jumping at very high speeds, your frequency, your optical frequency. And that can be a huge problem for entanglement rates with high fidelities. And that's something that is a big problem in the field, actually, right now. Robust emission enhancement, being able to do this actually properly with the right percent enhancement and in many cavities at the same time, making singles deterministically and spin controlling singles. And who's going to do that? My students. So yeah, I wanted to bring here these people, Christian, Elena, and Matteo, because we are working on some of these things. And I think especially if people have questions and they want to talk to someone, I think it's great that you know who they are and that you can chat with them and ask them the questions that you may not dare asking now. Okay, so the next step, and these are going to be fast. I hope, I actually don't know how much time I have. Okay, still some time. So I'm going to be talking about switches and filters. I'm going to combine them in one, and then I'm going to be talking about detectors. So what do we want from what I call reconfigurable photonics, which combines filters and switches in general from that photonic side? We want to have low loss and low power switching, and I will explain why in the next slide. We want to have on-chip filtering because we are getting a lot of different wavelengths of light and different laser powers in these chips to excite the color centers, and we need to be able to filter those out. Because otherwise, again, if you remember, the heat out detector is a problem, right? So we want to make sure that they don't. And we want to also develop photonic circuit architecture so that we can actually do these protocols in the cleverest way with the components that we have. So I'm going to be focusing on the first two, because that's what we have been working on so far. And I'm going to give a little bit of motivation of also one of the answers that you gave when I asked about color centers, asking about do we have everything we need, right, in terms of components? The answer is not really, and you can see one of the reasons here. So let's say we have a very complex photonic chip, the ones that I said that you can actually buy from a foundry. You can tell them, I want to have this chip that has all this super complex circuit with all these switches in between and all stuff, right? Something that looks like that, some sort of very complex thing. In this case, you really want to go quite complex. You want to go for 10,000 of these reconfigurable elements. So basically 10,000 switches in your circuit, right? So you want to do something serious, right? If you put that in a cryostat with today's switches, that would mean effectively having like 2 of your home fridges dissipating heat inside your cryostat in a 1 centimeter square chip area. I guess quite some people here work with cryostats. You can imagine what would happen to your cryostat if you do that. Yeah, it's going to be probably hotter than outside right now. It's going to be probably melting part of your cryostat. You don't want to do that, and that's a problem. And that's because a lot of these switches today, actually the main switch technology today that are using photonics is based on heating, literally heating, right? So you don't want to do that. You don't want to have that on your cryo. So the way we fix that, even before I knew I was fixing this, this is actually one of the first devices that I fabricated during my PhD. It's kind of fun to bring it out here again. And when I checked the time that we published this was 10 years ago, which makes me feel quite old. This, for the people that are not familiar with photonics, you have these kind of brighter areas here. These are waveguides. So this is where the light travels through. So we can send light through here, and then it goes through this straight waveguide. And then this is a ring resonator, meaning that there's some coupling between this and this, and then you get some light traveling through and resonating at certain frequencies, certain wavelengths, and then it goes up there, or the one that resonates kind of gets lost. Now, this ring resonator has something special, which is this little ring here, and this whole area is actually floating. It's suspended like that. So it's actually cantilevered away from the substrate. And then when you're looking at there, the whole thing is silicon, and the substrate is also silicon, and you can bias it. It's conductive in some way. So by applying voltage between the device, the top layer, and the substrate, we can actually move this. And these are some pretty cool pictures that I took in the SEM. The reality of this picture is that it's completely broken. So I actually was charging it with the SEM and I collapsed it. But it gives a pretty cool impression, I think. In reality, this movement is going to be much smaller, right? It's going to be within like some hundreds of nanometers or something, right? And that's enough for what we want to do. But in this case, it's you can see it kind of exaggerated by the device actually being broken. By doing that, what you're doing is you're effectively having a phase shifter inside a ring, inside a resonator, right? So you are basically you're changing the speed of light a little bit through the amount of silicon that the light sees as it travels through, and that changes the phase of that light, and that changes the resonance frequency of your resonator. And this is something that we see if we look at the data here. So this is a similar device. You can see resonances, right? And then in this case, in this zoom in, you can see how these resonances shift as we apply a voltage. These are different voltages applied to to the device. So that's effectively just a tunable filter, right? Which is something that is quite nice to have. And it's working with MEMS, with microelectromechanical systems, with this capacitive, displacement actuation, which means that their power consumption is ridiculously low. You have basically a capacitor, and you are running it mostly under DC, and it's a high capacitor. So you really have very, very little leakage current. We actually couldn't even measure the power consumption of this when we were trying to measure it. It's going to be below the nanowatts for sure. So this was cool. We managed to do this. We managed to do also phase shifting, which is also the basic component that you need for all of this. And this worked out very nicely, even in commercial foundries, actually. And of course, the caveat here is that we're doing all of this at room temperature, because actually my PhD was on classical photonics, right? For classical technologies for internet and communications. Okay. So what are the remaining challenges? Well, the remaining challenge is to show this at cryogenic temperatures, right? To show that these things can also hold when you put them inside a cryostat. You want to make the right filtering for color senders, right? If you want to put it with color senders, you need to filter the right lasers, the right phonon sidebands or whatever you have there. And you want to build also architectures for color senders. And again, Yelena and Mateo come up here. Also, we have some collaboration with TNO on the people that are working in my group towards these next steps, towards solving these remaining challenges. Okay, the last part before everyone falls asleep. We have detectors, and I'm going to go quite quickly through this. So what do we want about detectors? We want detectors that have high yield, that we can make many, that are efficient, and that have low jitter, that in time-wise, they are kind of sharp. When they get a photon, you get a click. That's it, right? And the efficiency is, if you really want to get a click every time you get a photon, you may need to operate them under magnetic fields, and you want to protect them from also this unwanted light that we were talking about, right? Of having stray light just hitting your detectors when you don't want that. And this is a picture schematic of one of these detectors that we are using, which are superconducting nanowire detectors. They are effectively just a very thin superconducting film that is meandering like this here. We bias it so that it's very close to the superconducting to normal transition, which means that then when a photon hits, if it's small enough, the area there, you traverse that transition, right? You go from a zero resistance to a very high resistance that gives you a pulse, right? That gives you a very efficient detection. And this is something I have been working on for a while. I'm going to be focusing on that first challenge. And I have a bunch of work here, but I didn't want to put all of it because I thought it was too much. So I'm just focusing on the very recent work that we got out and we are fighting to get published now. And that is putting these superconducting detectors into any photonic circuit. One of the issues of the field is that these detectors, they need a very specific or relatively specific material properties, right? So for example, especially with the materials that we work, which are niobium nitride, niobium titanium nitride, you want to have quite amorphous materials. And then depending on which material you're growing it on, you may have issues, right? You may be growing it on a certain substrate that may make your detector just worse because the material quality ends up being worse because of growing it on that substrate. You may want to put detectors on chips from foundries that they are not going to care about making a superconducting detector for you, but you may want to put them afterwards, for example, right? And this is a problem, right? Because you can get on one hand super complex photonics, but you cannot put all the stuff that you want on them. So this is something that we addressed by working on this transfer printing of detectors. So we basically decided to fabricate the detectors on a different process and undercut them so that you can have them floating and easy to just come in and literally pick up and place them on the chips that you want them. And in that way, we can put them everywhere, right? So that we don't need to redevelop anything, we don't need to change anything. We just get chips. We just need access to the waveguides, right? So we need some sort of window, and that's something that you get in every foundry. And then we just take the detector and put it right? And then we can also pre-select detectors. This is also a big problem, that the yields tend to be kind of low, or around 50%. So you want to have all your detectors working, but when you make them, not all of them work. So you're going to also be selecting the ones that work and just placing them, right? And that you can make a very high yield circuit in the end by doing that. So yeah, we do that with transfer printing, and we managed to get superconducting detectors onto 2 photonic platforms, and actually we have a few more there, but what I'm showing here is in silicon. So we did this process, we transferred them, the detectors with their superconductors on top of silicon waveguide, and we see that as we bias a certain current, we get this plateauing here, which means that the detector is actually working with unity internal efficiency, meaning that every photon that gets absorbed by the detector gives you a clip. And this is a telecom in silicon. We also did it in materials like lithium niobate and so on, which are materials that are known to be very hard to work with. Okay, so that's all I have for superconducting, for single photon detectors. What's missing? Actually, one issue that I didn't mention in the previous work here is that because of the design, the photonic design of this, that was a little bit hastily done by myself, actually. I can only blame myself here. We only got up to 10% efficiencies of detection efficiency, meaning that if you have a photon coming through this waveguide, then only 10% of them get absorbed in the detector. And this is just a photonic design. There's nothing fundamental about it, but this is something that has to be worked on. We had some issues with jitter also in this detector, so something we have to work on. And they have to operate under magnetic fields, as I mentioned before, and you want them to be protected from this unwanted light from color centers. So this is all remaining challenges that need to be tackled. And we are doing some of that in collaboration with the group of Ryoichi Ishihara. I think there's no one of these people here today, but Marie and Lynn are working on this, trying to solve some of these problems. All right, let's conclude with another question. And it's actually the same question than before. It only changes the last. And it's a question to see whether you were paying attention, actually. Okay, let's see. Nice. So 30% of people get more the coffee. I hope there's still some left. You guys know you have free coffee, right? In QuTech. They host qubits with long coherence times. Nice. They give us high entanglement filters and photon loss. Good. Many people are answering that. This is the case. Of course, I haven't shown that. But this is, at least theoretically, this is the case with these algorithms that we are using, or these protocols that we are using. I like that people pull back from color centers are great photon emitters, because they are photon emitters, which is nice, but they're not great. And this is something that we really fight with. And that we have all components we need for complex quantum systems. That's part of the job here. And this is where I hope I have transmitted to you guys that this is something that we are working on, all from the engineering and from the science sides. So let me conclude quickly. So color centers in silicon are promising for quantum information processing. So they have this telecom optical interface, they have long spin coherence, and they are in silicon, which is very nice. So it allows you to do a lot of these experiments relatively quickly and in a very nice way. We have started developing some of these building blocks. And these are schematic of those. And there's still a lot of work to do. But we got good people on it. So with that, I would like to acknowledge a lot of the people that did this work, both at KPH and at MIT, especially at MIT. A lot of these people are first authors or second authors of these papers. I would like to also thank my group, which is the good people that will crack this puzzle, the ones that have to deal with the actual hard problems. and to my sponsors. Thanks a lot for listening, and
it's time for questions.
yeah.
Thanks for the great talk. I want to ask about your solution to the genius line with. Just curious the way, so by applying the voltage, do you then create a more or less similar strain to different color centers such that they come
So I may not have explained this very clearly, but one of the ideas at least for this is that, let's say you have a color center here, or like each of you have one color center here and one color center in the same device, like another copy of this device with another color center. Right? In principle, when you make them, they're going to be different, right? They're going to have a different coherent emission line width, right? And then by doing this, then you can tune one to the other, for example, right? And then you will align them. And then if those two color centers are going into your entanglement station, right, or your beam splitter and your detector, then you should be able to get to improve the fidelity of your entanglement rates. Yeah. Thanks.
Yeah, go ahead.
Apply the the voltage of the electrode. How fast the beam could bend? Because it is not like needed like the others can go to the organ.
So you're saying that because silicon is not a conductor, right? You can have limitations on how you're doing this. That's correct. Yeah. So in principle, at room temperature, this works nicely, right? And also at cryogenic temperatures with this. But it's true that you do have some limitations in terms of speed because of your relatively high resistivity, especially if you move to potentially more even pure silicon without absolutely any doping. You probably will start running into issues because your resistivity may be too high for doing this. And then you probably need to play some tricks, for example, partially dope it. This is something that you can do. A lot of these things, you can do them in such a way that you don't affect the optics or the color centers. You can be clever on the way you're designing your device, that you can have part of it that is actually shows a nice conductivity and part of it that maybe doesn't, but it has your color centers and hosts your optics. Yeah, but it's a good question because it's something that we actually didn't know how good it was going to work at cryogenic temperatures, but I think because of the background doping of this, which is kind of commercial silicon, actually, it's the standard kind of silicon photonic layers, and also the carbon doping that we have for the color center, is probably just adds up to a pretty decent conductivity at cryogenic temperatures. Yeah. Yeah, okay, I didn't explain that. So in general, doping can give you losses in optics, right? You can think of, depending on the doping that you're applying, you can have sort of free electrons, right? The more electrons you have there, or carriers that you have there, then those can be excited by the light, and then they can give you absorption, right? So then in general, a common guideline for working with photonics is that you don't want to have doping very close to your devices unless you can live with a certain amount of loss, which in classical photonics may be okay. In quantum, is maybe a little bit trickier. Yeah. Mm-hmm. Yeah, so it's right that, so depending on, one way to think about to see this, maybe let me rephrase a little bit your question. So depending on the color center orientation, right? In this case, especially with these low, I didn't explain it, but these are pretty low symmetry color centers. So you can have many different orientations of them, right, in your crystal. depending on the orientation and the direction of this train, you can have a very different effect. And you can actually see a little bit here, right? You can see how this one is not shifting so much, right? Whether these ones are shifting in different directions, right? And this is partially because of the orientation of the color center, also because of the position in the z-axis, which is another question here. So yes, that is right. There are ways to go around it, though. So if you think about the way this works, it's a rather simple device, and actually we designed this device to be able to actuate it also towards this direction and towards this direction. So you can actually have at least those kind of 3 different degrees of freedom that will allow you to, no matter where the color centers are, to tune them in different orientations. So you could go negative to positive in that axis at least. Yeah. Yes.
Maybe there was a question online.
No.
No. Okay, good. Then with that, if there's no more final question, let's thank Carlos again.